Hello, everyone. This is Spencer Snowling from Hatch, and I'd like to welcome you to this month's GPSX webinar. It's the first one of 2023. I hope you had a good holiday. So today we're going to be talking about how you configure biological nutrient removal systems in GPSX. So it's quite a common thing to model the activated sludge process and to use the models to analyze and optimize BNR systems. But there's a lot of settings to consider, and so we're going to go through a lot of those today. I'm happy that you're able to join us. So I'm going to start out with a little bit of discussion about BNR systems and how you would lay them out on a GPSX drawing board, and there's a number of decisions that you can make along the way. And then I'm going to run some simulations. I'm going to actually build an A2O system from scratch in GPSX and put a number of graphs together and so on, so that you can see the experience of doing that and go through the decisions that we're making to sort of make it as easy and useful as possible. Then we're going to use that model to optimize the design a little bit. And then I'll come back and give you a few helpful tips, various things that we've learned over the years about how to use some of the GPSX features to make your life as easy as possible. One of the key things that's so great about these models that we develop is that they have a huge amount of information in them. So we want to not just throw out every single thing on a graph. We want to be able to represent the information in the most useful way possible. And over the years, over all the releases of GPSX, we've put in quite a lot of interesting features to be able to do that. And I think some of them maybe not everybody knows about. So I'm going to try and point out a few interesting things that you might not have seen before along the way during my desktop demonstrations that we're going to do today. So as per usual, we're always happy to answer any questions that you might have. So as they come up to your mind during the webinar, you can type them into the questions box that is part of your GoToWebinar dashboard. So pop that open, type your question in there. And so what we'll do is I'll just keep moving along through the webinar. And when we get to the end, I will stick around after the end of the webinar to answer as many of those as I can. Okay, so on to talking about BNR. So just for clarity, I'm talking about biological nutrient removal. So basically designing activated sludge systems for the removal of nitrogen and phosphorus. And of course, some COD will go along with that as well. These are conventionally a number of tanks in series that are under different conditions, anaerobic, anoxic, and or aerobic conditions. And they're usually a bunch of tanks in series with some internal recycles from the end of the system back to the front and so on. And the various systems are designed to do different things in different ways. Some are more efficient for different types of influence than others. But generally the idea is you're going to have a bunch of CSTRs in a row that are of different conditions. And when the biomass moves through them, hopefully you're going to get the right kind of growth under the right conditions to sort of optimize the removal and conversion of various forms of nitrogen and phosphorus. Now, it's really useful to model these BNR systems because they have a lot of degrees of freedom. There's a lot of moving parts in this kind of a thing. You might have 3, 4, or 5 different reactors that are there in series, and they might have a bunch of internal recycles. They all have their own DO settings, and the tank sizes, the size of the relative sizes for each of these things, the anaerobic anoxic zones and aerobic zones and so on, are very important in the design. So there's a lot of things to be considered, and having a model allows you to investigate those things very easily. The good part about all of this is the IWA style ASM models that you see in GPSX that were based upon that ASM1, ASM2D type of approach from 30 years ago. They capture nitrification, denitrification, and EBPR or BioP processes really well. I mean, that's exactly what they were designed to do. So those approaches have been tried and tested and well calibrated over the years to be able to accurately switch to different types of growth depending on what the conditions of the reactor, whether it's anaerobic or anoxic, for example. And also we have really good understanding, I think now, of what types of biomass are growing under what conditions and what the stoichiometry of those things are. So the models are really useful for doing that type of design. So those original models, like ASM2D, have now, of course, been expanded and improved upon over the past 20 years. And our Mantis 2 model in GPSX has been around for almost 15 years now and is extremely well calibrated and well tested to be able to do a full suite of BNR systems. And we actually have 10 different biomass types and a huge number of different types of substrate that are there. And so we want to be able to, through today's webinar, help you set it up to take advantage of all of that background material as best you can. Okay. So configuring the BNR layouts on the GPSX drawing board. Now, there's a number of decisions that you'll need to make along the way. And the very basic one to start with is there's really two different ways that you can go about laying out the reactors. One of them is to do it as individual CSTRs. So if you open up the GPSX process unit process panel on the left-hand side of your drawing board, you'll see various kinds of options for different reactors, including CSTRs and plug flow tanks. So if you grab a whole bunch of these CSTRs and draw them out like this, in the way that, of course, makes a lot of sense, you can totally do it this way. The other way to do it is to use a single plug flow tank. And in that case, the plug flow tank represents a number of CSTRs in series, and you can set them to be any number that you like. So these are two completely equivalent ways of doing it. It's really just about how it looks in terms of the information that you're going to display and the way that you're going to tell GPSX how to set things up. Underneath, it's exactly the same model. And then if you were to set all of the inputs in this section here to the same inputs as in this section down here, you will get mathematically exactly the same answer. So there's no difference in the process part. It's really just how you choose to lay it out on your drawing board. Okay, so just to reiterate, the plug flow tank by default is 4 reactors in series, but you can actually make it any number of reactors in series that you like, all combined together into one unit. Okay, so that's the one that I normally use. I tend to focus on using the plug flow object. You know, sometimes might combine it with a CSTR up front or something like that. But for the most part, I like it because it's a little easier to configure. All the settings are together in one place in one menu. So for example, if I wanted to change around some aeration settings and I had to go to each individual aeration menu, that's a little long and cumbersome compared to just opening up one menu and then they've got all of the set points there together in one place. It also saves some space on your drawing board. So if you're modeling a relatively complex facility, it might be useful to be able to just to have enough space on your drawing board, combining a bunch of units together. But one other key thing is that generally we have better default values for the aeration settings in the plug flow system, because these are sometimes things that change along the length of a plug flow tank. So particularly a good example would be alpha, aeration alpha for fine bowl diffusion. So you can see here that we're showing that we actually have a default setting of 0.4 all the way up to 0.6 as you go through the length of that plug flow tank. If you did it with CSTRs, you would get 0.6 in all of them. Now, that's fine. You can go ahead and change it as you like, but just to let you know that it's a little bit more sort of set up for you in a plug flow system. The other advantage is how we look at the output. So in your GPSX drawing board, when you put down a number of CSTRs, so here we're seeing the anoxic tank followed by 2 aerobic tanks. By the way, the aerobic tank can be set to also be anoxic just by turning off the air in it. We've put these together like this, and there's an internal recycle here. And I've done the same thing down here with just the plug flow tank set to 3 reactors. Now, if I wanted to plot, say, for example, the ammonia, here I actually have to drag each of the ammonia concentrations onto the same graph, and they would come across as lines like this. Whereas in the plug flow tank, we have that option, plus also the option to do it as a bar graph. Basically, we map the concentrations from each reactor into a single array variable, which then you can drag to a bar graph that looks like these. And so I find this to be a much more intuitive and easy to use and understand way to investigate the output from the model. because these BNR systems are almost always like, 3, 4, 5, 6 tanks in series, these bar graphs are kind of exactly designed to be able to make it easy to understand what's going on. So you can actually go to the output variables menu, to the concentrations menu, and plot any concentration that you like. There's dozens and dozens of variables there that you can plot. And also ones that are not concentrations. You can dig into the physical details as well and see things like airflow, OUR, oxygen transfer rate, pH, alkalinity. All that stuff is there for you to display. I kind of like the bar graphs as a nice way to look at it. I find it's really actually intuitive, particularly when you're evaluating operational choices or design choices, and you're doing that at steady state, and you want to be able to instantaneously see the results. So if I was looking at how does the internal recycle change the profile of these nutrients here, I like putting them all side by side here, ammonia nitrate, nitrite, and then changing that input variable, running it again, and seeing how these bars will go up and down. It is really good for being able to intuitively show you what's going on. I like it as a good visual descriptor. Okay, now, just as a counter argument, however, when you lay it out with individual reactors, it does look a bit more like a schematic, like a process flow diagram. And so maybe that's also an advantage in that sense, that somebody could say, well, I'd like to be able to see all the different parts. That is totally fine, totally valid. You do whatever the thing is that's best for your understanding of what you're working with. And I guess I'll just wind that up by saying, both methods are equally valid. It's just whatever you prefer. Okay, so once you've decided which way you're doing it, one question is, how many reactors in series should I be using for this? And there is no hard and fast answer to that. However, it is a function of the BNR design that you were doing and the way that it's going to be operated. So you need to pick enough zones in series to allow some flexibility to get the right number of anoxic and aerated zones, the way you're going to move your internal recycles through, and also reflect the geometry of the tanks a little bit where needed. So, for example, you have sort of 3 passes in an MLE zone, right? So you have, two passes in an MLE zone. You have an anoxic section, and then you have an aerated section. But in the A2O process that I'm going to go through here with you before, you actually have to have an anaerobic zone, followed by an anoxic zone, followed by an aerobic zone. So you need at least 3 in that case. So it's really kind of there to allow you, you're going to have to choose to sort of define it in a way that allows you to define those zones separately from each other. Especially if you're using a DO controller, there's only one set point for each zone. So you may need to break them out in order to have better control over setting those set points and setting those internal recycles. And then on top of that, any place you'd have like a really long plug flow reactor, it's a good to maybe break it up into a few. So I've been to a couple places where when we got to the aerobic zone at the end, it was actually quite long and skinny, 4 times longer than it was wide. So that is a little bit plug flow. So we kind of broke that up into 2 zones or 3 zones sometimes. So it's kind of a bit of an art, but those are things that are required for you to be able to set it up the way that you want to. If you're looking for some actual hard field measurements that you could do, tracer tests are a way to do it. You put in a sort of a conservative, non-destructible tracer that's going to go through your plant. You just sort of do it as a slug, and then you watch the concentrations in the effluent as they go up and down over time, and then you can calculate from that curve how many tanks in series your system acts like. So I have to admit, I can only think of like one project in my whole career where I actually did that, but nonetheless, so. Okay, so now you've decided which way you're going to do this, and you understand what you want. You've decided I'm going to lay out this A2O process, and I'm going to do it with 3 zones. Now there are 4 major settings that you need to consider when you're putting together your drawing board from scratch. The first is, how does the flow get into the reactor? Your distribution of the influent flow and the recycled activated sludge, the Raz flow that comes into the system. There's a bunch of settings for that. You also need to decide how I'm going to set up the reactor or zone volumes for each one of those parts. Also the aeration settings throughout the length, and also then my recycle flows. That includes both the way that the Raz comes in and also any internal mixed liquor recycle. So from, say, the end of the aerated zone to the head of the anoxic zone for doing denitrification, those are all things that are important parts of BNR that you need to specify correctly in your system. So what I'm going to do is I'm going to show you some slides on each of these 4 things, and then we're going to go into a desktop demonstration where I'm going to build one of these things from scratch. Okay, so let's start with the Influent and Raz distribution. So this is a plug flow tank object in GPSX. And so you can see here, of course, this is the influent connector part. So all the flow that's coming from your units upstream of this, so probably your primary clarifier, effluent will come in here. And then this is the effluent. This is where the mixed liquor will go into the secondary clarifier. And this is the Raz connection. Now, you may know that if you try to swap these around, it actually won't work in GPSX. You won't be able to connect something down here. The reason is the Raz has a little bit of a special solver included in it for doing proportional recycles. So that's why we like to have always bring your Raz into the bottom one and the influent into the top one. So by default, 100% of the flow will go into the first tank like this. So that's the default. And now this is a place where you may need to come in and change something there. So if you go to the input parameters menu, go to the operational settings, and then scroll all the way to the bottom of this menu, and then you will find the flow distribution settings here. Hit this button, and then you'll get a table that looks like this. So this is our 4 reactors that are in series. So this is the front. And we can see here that 100%, this is a fraction between 0 and 1, 100% of it is going into the front end of the tank. This is where we specify how we would like that to work. Now, if I wanted to do some step feeding, for example, where it looks like I have a sort of the flow spread into each of the tanks, so we're going to split it evenly across each of the 4 tanks, then that would look like this. So it's pretty straightforward. Just need to know that you've got to go to that influent fractions thing at the bottom of the operational menu and then go from there. So those are settings that are important to know. And then secondly, the Raz distribution is almost exactly the same thing. By default, 100% of it goes in the front. But if you have a situation where you would like to put it into some of the other parts of this system, that's this menu here. Same menu we were just looking at, but now this right-hand column here where you set your recycle fractions. I have to say, I haven't worked on too many systems where the Raz doesn't go in the front, but I can think of at least one where we did. But excuse me. Okay, so now if you're working with the individual tank method and not the plug flow tank method, then the influent Raz distribution basically is controlled with flow splitters. You'll actually be able to see it actually on the drawing board because each of these things are separate from each other. So our recycles here, if I wanted to do something where I was going to take some of the flow and put it farther downstream, I would need a series of splitters to be able to do that. So here I would put a 3-way splitter here. Some of that flow would go into the first tank, and then the effluent would come out and combine with some of the flow going into the second tank, and then the same thing for the third tank. So a lot more stuff on your drawing board in order to be able to do the same thing. Works out to a mathematically equivalent, the same thing as what I showed you before. So whatever is your preference, you can do it that way. Okay, so now that's the first step. So that was influence specification and distribution. So now moving on to the second thing was how do we set the volumes of all of our systems, right? So basically that is a menu. All the volumes are set in the physical menu. That's where we're specifying the size of things. And so if you open that up, the very first thing you need to do is change this thing here, number of reactors in series. So it's going to be 4 by default, but you can change it to something else. So I've changed it to 3 in this particular screenshot. And then you can go to this volume setup method here. So this is a way, 2 different ways that we allow you to specify the volume. The one that is used most often is volume fractions. So in this case, you're setting the total maximum volume. Then you have a button here that allows you to specify for that total volume of all the reactors, what is the percentage for each reactor. So here, this is 1,000 meters cubed, and it's evenly split across those 3 reactors. Now, when we go into the desktop example, you'll see how I'll play around with this kind of an idea. The other option is to go to individual volumes, and you just hit this button and you just type the volumes in directly rather than the total and then the dividing it up. Now, why is that useful to do it the other way? It's actually useful if you have a BNR system where I've kind of already set it out. I know I want 60% aerated and 20% and 20%. And then, but I just want to scale the whole thing up and down without changing the relative proportions of everything. That's why we've done it that way. So anyway, those are two options that you have. Okay, that's two of our four things done. On to the third one now, the aeration settings. Those are the things that are going to control, how much oxygen is there, which therefore controls whether this is an anaerobic anoxic or an aerobic system. So same menu as we were just looking at, input parameters, operational. And so then here is where you'll find all the settings for the aeration. The most important thing to look at is whether you're using a DO controller or not. So if this is going to be set to DO control by default, it will have the controller on. And then you can go to that button down there at the bottom, and then you can set the DO set points as needed here. So this, for example, has an anoxic zone at the front, followed by 2 aerobic zones. So that's kind of the handy way to do it. If you're doing like a design level thing, almost always it's easier to just work with the DO controller on and just let it give whatever airflow it needs to meet that set point while you're in the process of trying to design your thing. If you can then figure out, okay, how much air was required and can I make it better, that's the second step in the process. Excuse me. Okay, so now the other option would be to turn off the DO controller, put on airflow, specify the total air, and then the amount of air that goes into each tank, right? So you could taper the system so more air is up front and less at the end and so on as needed. Okay, so I'm not going to go into a great amount of detail because we actually have a really good webinar on this already. So I highly recommend going to our modeling aeration systems. I believe it was April of last year, where we spent a whole hour talking about how to use all of these features, how our models work, how we calculate the saturation concentration of oxygen and all that kind of stuff. So hit the YouTube channel and check this out, and that'll give you everything you need to know about aeration in GPSX. Okay, that was the third, and now we're on to the fourth and final thing that you need to set up to do a BNR layout, which is the internal recycle settings in the operational menu. So internal in this case means internal to that particular object. It's from one zone inside to another zone. So you won't actually see anything when you use the plug flow object itself. It's talking about moving from the third reactor to the second reactor, et cetera, et cetera. So go to the input parameters, operational menu, slide all the way down to the bottom again. So we talked about flow distribution before. Now we're talking about this internal recycle settings button. When you hit it, you'll get actually this custom made menu that we have. Looks a little different than a lot of the other ones. The key thing is you need to know I'm going from a tank and to a tank. You can specify up to 10 different recycles. They'll go from tank 3 to tank 1 in this particular case, and then you can set a constant flow rate if you like. We also have the option to do a proportional recycle. So if you do that option, this thing gets grayed out, and then you get a recycle ratio, and then this opportunity here in this window to type the label, the GPSX label of the connection point where you want to make the flow proportional to. So for example, typically you would put here the influent label, the label of your influent object, and then GPSX will set that flow times this recycle ratio, and then that becomes your internal mixed liquor recycle. Right, okay, so if you're using the individual method, then you just draw the internal recycle right on the board. That one's pretty straightforward. It becomes a little complicated, and you get a lot of stuff happening on your drawing board. If you have a very complicated layout, you might have recycles crossing over each other, for example. But again, totally valid way to do it. You'll get exactly what you want, and this way it shows it a little bit more explicitly. So you control the flow rate from that pump connection point. So open up the operational menu, and it's down here under pump flow control. So we're going to go on to a desktop demo. So as I mentioned, we're going to build an A2O process, and I'm going to lay this out for you, and we're going to do those 4 parts. So I just thought I'd do a real quick summary of what the A2O process is. This is for doing biological phosphorus removal. So this is a system that promotes the growth of phosphorus accumulating organisms by having an anaerobic zone and then also an aerobic zone. So we'll get the PAOs, they'll suck up the phosphorus and then be able to be settled out in the clarifier and removed. At the same time, this process also does nitrogen removal, and the aerobic section will have nitrification happening, and then there will be a recycle to the anoxic zone where they'll have denitrification. So we're getting rid of both nitrogen and phosphorus all together in this same process. So the influent comes in here. We have a secondary clarifier with a typical recycled activated sludge. So this is going to go all the way around to the front of the system, and we're going to waste from over here. And then there is this internal recycle. So this is the part that's helping with the denitrification. So at the end of the aerobic zone, when it's gone through this nitrification, ammonia has been oxidized to nitrate. That's going to come back over here. And we dump it in the front of the anoxic zone, where it will go through denitrification from the heterotrophs. So, okay, so now we've got that all set up. We're going to do this, and this has those 4 elements that I mentioned before. We're going to have to make decisions about where the influent goes. We're going to have to set these tank volumes. We are going to have to set some some aeration settings to make sure these are all what we want them to be. And then we're going to have to specify this internal recycle. So the same 4 things that I just went through in the slides. Okay, so let's go to GPSX here. Now, I already put down an influent and a primary clarifier here. This is more or less our default settings. I did change the influent just a little bit. I made it actually a little bit more fermentable substrate here, or fermented substrate, because that's actually required for letting the PAOs grow. And I didn't want to get this all hung up on influent characterization. So I've set it up with an influent that kind of works nicely. Okay, so now the next step is to lay out those reactors. So as I mentioned, they're here in the suspended growth process. We have these completely mixed aerated ones, some completely mixed anoxic ones, and then our plug flow tanks and so on. We could, if we chose, to do A2O, do it like this, put this here and here and here, and then we could hook it all up so that we had everything that we needed in line, and then we would set the sizes and whatnot, and this is what our internal recycle would look like. However, as I mentioned, I don't like to do it this way, mostly because I want to take advantage of some of the other features that we have. So let's not do that. Let's actually do the plug flow tank option here. So we put that on there, and then we need a circular secondary clarifier and an effluent. So I'm going to build all of this out from scratch as we go here. So I'll try and keep it as simple and straightforward as I can, but bear with me. There's a little bit of fiddling here and there to do with setting up the graphs and so on. So I'll try to keep it interesting and moving along. Okay, so now we've got this very simple system set up. And then now we need to make some choices about where we want the system to go and to go through those 4 steps in the process. So save this first, and then what I'm going to do is that first step is how does this influent come into this system here? So if I right click and I go to operational, as I mentioned, slide all the way down to the bottom of the menu, flow distribution, and actually I'm going to switch this over to percent here. It's a little easier to read in my opinion. Influent fractions, 100% of it goes in the front. Oh, you know what? I skipped a spot. I forgot. This is showing 4 reactors in series. So just let me back out here. This needs to be 3 reactors in series. That's actually right here in the physical menu. So what we need to do is now we'll go back to the influent part and slide down to the bottom. And then now we'll see that we only have 3 reactors and 100% of it is going in the front end here. Okay, same thing for the Raz. When we that connection point that's on the lower side of the left is coming in, that's also 100% of it goes in the front. Okay, so no changes to be made here, but we did check, and this is where you would make the change if that was part of your BNR design. Okay, so we got that part set up. Now we need to go to the next step, which is to set the volumes of these 3 reactors in series. So I'm going to go back to the slides for a second and show you one way to come up with what those might be. Let's move on to the next slide here. So, we could make a half-day course out of how to size BioP reactors. And so it's not really the focus of today. So I'm just going to show you where I came up with some numbers. So I went to my trusted Metcalf and Eddy textbook, and I grabbed these numbers off of one of the tables for A2O that says, here's some rough residence times, and we should be shooting for this kind of mixed liquor here, retention time, and so on. And our Raz and our internal recycle flow. So these residence times will then tell us how big the facility should be. So you can see here that there's actually quite a bit of variation. There's a lot of fairly big range in a lot of these. So just for the purposes of illustration today, I just took something right down the middle. And I basically took an average of the high and low just to put something together and allow us to proceed. Now, as I'm sure you can imagine, this means it's not optimal, right? I just took an average. So, and that'll allow us a little bit of room later on to actually fiddle with these numbers a bit and then see if we could make things better. But just for the purpose of getting things started, let's just go straight down the middle of the plate here. So for an influent flow of 2,000 meters cubed per day, that's going to give us these numbers here. So 85 meters cubed, 65 meters cubed, and 500. And then we got our Raz, 1,200 meters cubed per day, and 5,000 meters cubed per day for the internal recycle. All right, so we've got all of those numbers. And so let's put those into GPSX now. So as I mentioned before, there's a couple different ways to do this. I'm going to do it via the volume fractions method. So here, this needs to be 650. That was the sum total of those three numbers. And then I can set this up. So you may have seen on that slide, let's do this as percent. It was 13.1% for the first tank. And then the second tank was exactly 10%. And then the third tank was all the rest, which is 76.9%. And then now we're set up with all of those at the right volumes. So that's that second step in our 4-step process. Okay, so that's set up now. All right, so then the next step after that is to set up the aeration settings. So that is again in that same menu, the operational menu. And if I go to this menu here, I'm going to leave the DO control on, as I suggested earlier, and I'm going to go to the DO set point. So there'll be 3 of those, and it's going to go 0, 0, 2, right? So, oops, 2, because that is anaerobic, meaning no oxygen, anoxic, also no oxygen, and aerobic, we're going to have its DO set point of 2. So we're going to provide enough air to get to 2 milligrams per liter. Okay, that is that step done. And then the last step is to do our recycles. So the last step in that process is to set the internal mixed liquor recycle. So this is the one where we have to specify from one tank to another tank. So I'm going to slide down here. This is this bottom one, internal recycle settings. And I'm going to use here from tank 3 to tank 2, meaning from the end of the aerobic zone to the beginning of the anoxic zone. And we're going to do it for 5,000, I think it was on that slide. Just let me check. Yes, that's correct. And we're going to leave that as a constant. So accept, and that's good. And then the very last thing we need to do is actually set the Raz rate. That was another number. We had 1,200 meters cubed per day, and that's in the operational menus of the clarifier itself. Just to be clear, this is the Raz coming around here. This is where we're wasting from. So let's go here. We're going to set this number to 1,200, and that is done. So that's all of the recycle settings. Okay, so now the plant theoretically would run as it is, but there's a couple other things that I almost always do when I'm setting up something like this. And one of those is to define an SRT for this plant. So as you may know, GPSX does not automatically assume an SRT for you. We actually ask you to come up to this button up here, the define function, and to define a solids retention time for this facility. So by that we mean we want you to tell us which things do you want to include in the SRT calculation. You can in fact have multiple SRT calculations here. We're just going to do a regular one here. So this is going to be our T here, and I am giving it a name. And then here you can see this is mass over mass flow. The way we go about this is to click on here. I want to include all the reactors. And then this is the connection point. That is where the wasting happens. So that's mass over mass wastage, which gives us our SRT. One other thing I'm going to do is actually turn this on. Estimate WAS using an SRT set point. So it's going to use this connection point here, and I want to set it for 15 days. And then now that's done. So what's going to happen now is it is going to set this flow rate here to whatever gives us 15 days of SRT. It's kind of like having a controller on it. Now, we've done that here because that's a really useful way for design to be able to keep an SRT at a given size, keep that as a constant while you're moving other things around in your design. Okay, what else is there? I wanted to have the pH on as well. So that's in our site properties menu here under biological model settings. Oh yeah, sorry, the pH is on already. By default, it will be off. When I rehearsed this earlier, I must have left it on. So I set this to estimate pH to have that on. Okay, I think everything else is pretty good. I'm going to save that as it is. And then I'm going to go over to simulation mode. And while that is doing its thing, this is now compiling the model, of course. Now, we want to be able to set up a few things that will allow us to run the model and to play around and do some optimization. So we'll put a few things up here that allow us to adjust those things that we were investigating, right? So one thing that we can do here is, first of all, if I right-click and I go to that physical menu that I had up before, let me move that thing out of the way. I think it's almost finished compiling. Yep, there we go. So that maximum volume and volume fractions can actually be put up here. So if I drag it and I drag that, that gives us now a way to adjust these things and test out and see whether we can improve upon and optimize our BNR designs. So we'll do those two. I also want to play around with the recycles. So let's do the Raz first. That is that same setting that I set before. This one here, the 1200. I'll drag that up there. And also that internal mixed liquor recycle. So if I go to the operational menu, we go back to that large menu that had the from and to and whatnot. And I'm just going to grab this thing and drag that over as well. Okay, so that puts us in a good spot to do everything. We can now do some analyses. Now, I should mention I'm only going to do steady state. Certainly, you can do all the dynamic simulations that you would like, and those would be an important part of your design. But for this 1 hour we have together today, I'm just going to stick to steady state. One other thing I'd like to do, just for the sake of aesthetics, is these percentages should add up to 100%, right? It's 100% of the volume here. But these things are not set to a maximum. So what I'm going to do is I'm going to just set these all to 100, just so that they're all proportional to each other. Doesn't really change anything in the model, just makes the position of the slider look a little bit more representative. So right now we're looking at 76.9% of the volume is aerobic, and a much smaller amount is anaerobic. All right, so let's just run a quick steady state solution and see where we're at. So I'm going to let that come to steady state. And right now I'm looking at the outfall tab here. And I can see that our TSS is 12, so that's pretty good. And BOD is less than 6, which is great. And then our ammonia is 0.3, so not bad. It's less than 1 anyway, so that's good. TN is 11, which is not too bad. Like our nitrate is 8, so we're actually doing pretty decent denitrification, or not bad anyway. I mean, it was like 30 coming in, so that's pretty good. And the most important one, though, is our BioP, right? So here's soluble phosphorus, 1.13. So that's okay-ish. And let's see if we can improve upon that. So as I mentioned before, we have a lot of tools to visualize all the stuff that's coming out of this model here. So we want to be able to sort of take advantage of that and understand all the other things that are happening in this system. So what I want to do is actually plot some of these bar graphs. And I'm going to go back here and just show you a couple more slides about this. So in any one of these plug flow tanks, you can right click on output variables and you can go to that concentrations in reactors. That's by selecting in the middle of that tank. And then now you have the ability to sort of grab anything that you find on that menu. And if you click on this button, you can get at the individual reactors, but don't do that. Just grab the actual words over here and drag that over to an open spot in the output panel, and then you'll get a bar graph like this. These are the most useful things, in my opinion, of how to do it. You can actually click right on the bars to get the actual values as you go along. If you're using the individual CSTRs, it actually is possible to combine them together in a bar graph via making a table. It's sort of an extra function that we have. If you want to be able to make a bar graph across the plant, across different unit processes, click on this new table tab button at the top of the outputs and make a table. You select which units you want and which things you want to graph from each unit. And then it makes a table that looks like this. But then you can click on this button right here, and then that will give you a bar graph. It's a way to get a bar graph of more than just the plug flow tank. But you can use it for that same type of process as well. Okay, so let's optimize this thing now. So can we improve this without sacrificing too much of the other stuff? I think our objectives should be, so let's hang on to the nitrification, of course. Let's keep this ammonia relatively low. Let's see if we can improve this, get it down to a lower number, and get that nitrate down to a lower number as well. So what that means then is we want to, here, let me delete this old graph. We want to plot some of those bar graphs that we had up here before. So I'm going to right click and go to that concentrations menu that I mentioned earlier, slide down to nitrogen here, and let's do ammonia, and let's do nitrate. And then I also want to do dissolved oxygen. It's actually here at the very top. And then I want to do phosphorus, orthophosphate. Here we go. Okay, so now we got those 4 bar graphs that are going to show us all of them in each reactor here. This button is a useful thing, auto arrange. If you haven't yet got used to that, it basically just resizes your graphs for you. And one other thing that I also normally do here, I actually have the default for doing auto scaling turned off. It might be turned on in your case, but I just want to rescale these, knowing that we're going to come to some better looking graph here, because otherwise it's going to be way too big for us. So what I'm going to do is I'm going to set these to 10 for ammonia. I'm also going to retitle this ammonia. And then I'm going to do the same for the other graphs as well. So this one is nitrate. So if I go to output graph properties, I can do the same thing here, nitrate. And I also want to set this to 10, and I'm going to set this to a different color. Let's make that one green. I think I left this one at yellow, didn't I? Yeah, okay. And then this is phosphate, ortho P. So we may need a bigger graph here because it's going to release first. So let's do let's do 50. And call this ortho P. And phosphorus, let's make blue. One of the really interesting things I've discovered over my career is that everybody has their own palette of what they think nitrate and phosphorus and oxygen looks like. And I have my personal one. I think oxygen comes out red. So anyway, let's put 5 here. This is our DO. Okay, all set, steady state, and we're running that again. And now we have our graphs that we can use to understand what's happening here. So in the system here, we can see, of course, that in that aerated zone that a lot of the ammonia here is coming down. It's being nitrified. There's nitrate is here. And so this is an effluent ammonia, or at least at the end of the aeration tank. We're assuming there's no biology happening in the clarifier. So this is the same as the effluent. 0.36, that's not too bad. What's our ortho P? We know it's at 1 point something, 1.15. So we're going to try and adjust some of this to make it better. So let's try. Oh, one other thing I wanted to do is actually make a graph of the SRT as well. So just let me make another tab. The way you plot the SRT, if you've never done this before, is to go back to that main menu and grab the name of the variable that you had and put it over here. I find it most useful to set this as a digital readout rather than a chart. We're not doing dynamics, so I'm actually going to remove that one. And also, while we're here, I'm going to throw the mixed liquor. So coming out of this tank, go to the concentrations menu, grab the mixed liquor and put that on there as well. Okay, so now we have this, and if I run steady state, I should get, there's my 15 days. That was something we set it for. Mixed liquor is 3266, so that seems reasonable. Okay, so here's our profiles again. Oh, no, that's not the profiles. This is the profiles. And here we go. All right. So now what we can do is, I noticed that, of course, we got lots of performance in terms of nitrification here, but these are actually relatively small amount of this tankage is available for the fermentation step, for example. So let's maybe increase this a little bit. So this all needs to add up to 100. So let's make this an even 20%. Leave that at 10, which means this has to be 70. So we're stealing a little bit of room from the aerobic zone and adding it to the anaerobic zone. And we're going to run that again. So, okay, not a massive amount of change. We're still okay here, but that has improved our P, right? It was 1.1 something before, now it's 0.5. So that was a fairly good improvement. So let's see if we can also improve the denitrification here. This is 8.4 for our nitrate. So if we make this zone bigger, our anoxic zone, then that might help. So let's steal another 10% off of the aerobic zone. So now it's 20, 20, 60. And run that again. And you can see that really actually did improve a lot. It went from 8 point something to 5 point something, right? So that's good. How's our ortho P? Well, it went up a little bit, but not too bad. No, sorry, that came down from 0.5 to 0.2. This is what went up, the ammonia, right? So ammonia is kind of creeping up a little bit. And of course, that makes sense. We've carved off some of the aerobic zone that was doing the nitrification. So that's cool. All right, let's see if we can push it farther. So let's see if we can get this down even lower. Let's give it a little bit more of an anoxic zone to get more release before the uptake. So that means I got to shave another 10% off that. And let's see how that goes. So are we still okay? 0.5, almost 0.6. Okay, well, we're still under 1. This is now dropping again. So that's gotten us below 0.2. And let's go just another 10% again, 30, 30, 40. That might be really pushing it, I think. Let's see, what did we get here? Well, it didn't, well, a little bit of improvement here. This is now at what, it's at 4. So we got under 5, so that's pretty good. And now we're at 0.8. Okay, well, if we want to stay under 1, we can't really push this too much further. So, that balance, this is a nice intuitive way to sort of play with these numbers while watching these bars in order to do that. So didn't really touch the other ones. We could increase the recycle rate. If I put it up to 7,000 from 5,000 and rerun that, that brought this way down again, right? So this is now down to 3.3. We were at 8 right when we started this process. We still okay here? Yeah, we're okay there. Are we okay over here? Yep. So that helped a little bit. We could even make the plant bigger. And so let's make this 800 in total, keeping all the proportions the same. And what does that do for us? 0.4. It didn't really make much difference. So this is an indication then of like one of these aspects here of this BNR system, playing around, making the plant bigger. That wasn't the problem, right? It's, we were a little bit choked off on the recycle, maybe, for example. Now, we could spend all afternoon iterating through this together, but just wanted to give you a flavor of what that looks like by playing around with those types of parameters and taking what is like a standard design and then putting it in the model and then really fine tuning it that way. Okay, so let me go back to my slides to kind of wind things up here. Oops, I'm on the wrong slide. Hold on one moment. Helpful tips. All right, so just to wind things up here, thought I'd point out a number of things that are very handy that you could do in GPSX. So for example, if you have to do supplemental carbon addition for denitrification, I recommend using the dual inlet plug flow tank. It's actually right below the regular plug flow tank in that process panel when we were picking them off the side there at the beginning. It has the same connection points as the regular one, except an extra one up here called Influent number 2. It's not really an influent, it's where you put in the chemical for this. So it would look like this when you were to lay it out. This object here is our COD chemical dosage object. It's found in the Influence tab. And so you would put that down here. And if you right click and open up the chemicals, you can see the various types of carbon addition that you can do, like methanol or glycerol, or mixed substrate is for things like micro C that are, the synthetic stuff. Now, the important thing is, just like the other Influent distributions, you need to come back to this menu and take a look. So previously, I showed you the menu that had Influent fractions and recycle fractions. Now we also have this Influent number 2 fractions. This is where you would specify where to put this carbon dosage. So in an A2O system, you would want it to be like this, because you would want it to go into the middle one, which is the anoxic zone, which is where the denitrification would be happening. Don't think our example was very carbon limited though, so we were doing pretty good. As you were going along using those bar graphs, you can at any time right-click in the middle of that graph to bring up this menu. That was the one I was accessing the properties from. And down at the bottom is a copy image to clipboard. It is like a super fast and easy way to get your images from GPSX into anything else. So I use a lot for putting them in an email or putting them in the report. And as a matter of fact, most of the graphs that you've seen in my slides here today have come via that method. Also, did you know that you can plot data alongside GPSX? Probably many of you have seen this. You can plot it alongside your model. This, where you have a spreadsheet which you associate with a particular variable, and then it reads all that in and plots alongside. Well, you can do this for bar graphs as well. And it looks like this. You see a sort of a shadow bar graph along with the one that is actually from your model. So in this case, the dark color is the model result, and then the shaded bit, the transparent bit, is actually your data point that you're reading from a file. The way to do this is actually to hit the data files button at the top of your menu, associate a particular spreadsheet that would have the data that you would want in it. This is basically the same as any normal data that you read in. It's just that if the data cryptic variable names that you got across the top here, these ones, those correspond to these individual bars. So that's a kind of a handy tool that I use once in a while. It actually also works for digital outputs, exactly the same thing. You can take a spreadsheet, read in these, and then they actually get plotted here and put in this table. So this would be a place you could put maybe some targets that you're shooting for, or some real data that you know that value is true. So I want to try and get my outputs to match that number. Right. Okay. Another useful thing is our visualization tab. So above your output tabs in GPSX, there's a little eyeball there, and that's our visualization tools. They're useful. This is where you can get a Sankey diagram. Now, the way that I find this useful is sometimes in these more complex layouts, you have to go in and set a bunch of pump settings and connection points and flow splitting and whatever. Kind of after I've got it done, I'll do one run of steady state and then plot the Sankey diagram just to make sure that these numbers are what I intended them to be, and that I didn't accidentally flip a splitter around the wrong way or activate the wrong pump or something like that. So these flows are basically the flows associated with each line. And there's also this little coloring here. The thicker the coloring, the bigger the number. So you can just double check, yeah, I got the right amount of flow coming to my digester, for example. You can actually do it for mass flows as well. This is, I find, really interesting. So here, for example, this is a 5-stage Barden flow. You can see that this is the mass flow of phosphorus through the plant. Of course, there's a lot of the phosphorus is being recycled around in the activated sludge part, but when we get to the end here, most of it is going to the solids handling side because we successfully had it captured by the PAOs and settled out. So of that 40 kilograms per day that is coming in at the head of the plant, 4.6 of it is going in the effluent, and the rest of it, 36 or 35 of it, is going out with the sludge the way that we would intend. So I find that to be a handy tool. So as I mentioned, Once you've gone to modeling mode and you have to have run a simulation so that you actually have some results, then this eyeball will become active, and then you hit it, and then you get various kinds of things. This is other stuff that you might find useful too: energy usage, operating costs, and so on as well. Right. Okay. So how am I doing for time? I've not left very many minutes for a question. I'll hang around for a bit so that we can answer some questions. But basically, yeah, setting up the sophisticated multi-stage BNR system is quite simplified in GPSX through using that plug flow tank object, but it's not required. You can break them out into the individuals reactors if you like. There's lots of output visualization options, bar graphs, Sankey diagrams, and various other things that you can plot and understand. As I mentioned, the models themselves has such a huge amount of information that you want to be able to dig into it, but you want to do it efficiently. I want to see the right kind of information. And so we've set up our tools as best as we can to help you do that. Whoops. And then lastly, once you get all that information in place, then, that little process I showed you about sort of optimizing, trying to get things, to the lowest level of phosphorus possible. Some of those bar graphs and other tools will be useful to help you do that.